Hi everyone. Today I will be talking about a very important topic in the automotive industry. I was wondering how those sleek aerodynamic wings on sports cars help with braking and overall performance optimization. Well, it's not just for looks, so I decided to see how this part affects the car. And there is no better tool than CFD. It's my field of expertise. And for those who don't know what CFD is, it is short for Computational Fluid Dynamics that uses numerical approaches to solve complex mathematical equations of flow and turbulence. Well, I will explore the science behind these designs and see how they can significantly improve stability, reduce drag, and improve braking efficiency. Firstly, I designed the car using a design modeler in ANSYS Workbench. Design Modeler is a software owned by ANSYS, and the simulation will be 2D to simplify things. I designed the car and the wing in its normal position. Then I subtracted them from the fluid domain. After meshing the model, I set up the simulation including the turbulence model and boundary conditions. For our case, we will work with a high velocity 100 meters per second because we simulate a race car at high speeds. I chose the scheme method, time steps and their size, iterations per time step, and then I did run the simulation. As in the previous steps, I made the design of the car, but with a vertical wing to see its effect on the parasitic drag. Following the same process, I meshed the model by setting the same parameters as before with the same boundary conditions. As you see, I chose a small element size in the regions where the flow varies little, the wing and the edges of the car. Then I run the simulation, and now we will move on to post-processing to see the results and analyze them. By analyzing the presented CFD results, we will examine the velocity, pressure, and turbulent kinetic energy to understand the aerodynamic forces lift, drag, and downforce caused by the car's wing. Starting with the velocity analysis, we observe that the velocity magnitude plot shows a high velocity region above the wing and a lower velocity region below it. The sharp gradient at the trailing edge of the wing indicates significant airflow deflection. The high velocity above the wing correlates with low pressure Bernoulli's principle, contributing to downforce. The increased velocity downstream reflects the wing's aerodynamic efficiency. Let's see what the pressure says. The dynamic pressure plot shows a higher pressure beneath the wing and a lower pressure above it. A strong pressure gradient is visible across the wing, particularly near the leading and trailing edges. This pressure differential generates downforce, pushing the car downward and improving traction, especially during braking or cornering. Moving to the turbulence. The turbulent kinetic energy highlights a region of high turbulence downstream of the wing. It is concentrated around the trailing edge, where the flow separates. Turbulence increases drag, which can reduce the car's overall aerodynamic efficiency. The well-distributed turbulence around the wing indicates controlled airflow, which is crucial for stable downforce generation. For the second case, braking, the wing is adjusted to maximize downforce. The velocity magnitude shows a reduced high-speed region over the wing compared to the earlier configuration. The flow slows down significantly after the wing, indicating stronger air deceleration and increased flow deflection. Reduced high velocity above the wing enhances the pressure differential, higher pressure underneath. This setup maximizes downforce, which is crucial for increasing traction during braking. The dynamic pressure plot indicates higher pressure beneath the wing and slightly reduced pressure above it. The pressure difference is more prominent. showing an optimized aerodynamic configuration for braking. Increased downforce enhances stability and grip during braking, ensuring shorter stopping distances. The higher pressure drag resistance to airflow may slightly reduce the car's speed. The turbulent kinetic energy plot shows high turbulence regions downstream of the wing. Turbulence intensity is more pronounced, especially near the trailing edge and in the wake region. The turbulent wake increases drag, helping to slow down the car more effectively. Controlled turbulence helps manage flow separation and maintain stability during deceleration. If we can summarize all this analysis, let's highlight the main differences from the normal case. The lower airflow velocity over the wing prioritizes downforce over aerodynamic efficiency. The stronger pressure gradient compared to the normal case highlights the role of the wing in improving braking. The increased turbulence in the airflow direction indicates increased energy dissipation, which contributes to increased drag and braking efficiency. In normal driving, the wing helps reduce air resistance and improve speed while keeping the car stable. During braking, it increases the grip on the road by pushing the car down and helping it stop more quickly. Overall, it ensures both better performance and safety. And it is not just for the look. Thank you, and see you in another video.